Yeah, right. Yes. You can still protect that he's still down. All right. Jingzi, do you mind closing the door? Oh, lock everyone out. There's a stopper. Okay, cool. Hey, welcome to our fall 2025 hackathon. So, gonna start off with like big thank you. Yes, yeah, I see the dot. Thank you. So welcome to our fall 2025 hackathon. Thank you so much for staying with us for the 5 days and doing some amazing work. And want to say a big thank you to Sarah, Anya, Naomi, and Grace. So they're back. So let's give them a big hand. Hi. For all your free food and cookies, right? Okay. So we also have 5 judges here. So we have Travis from TechDot, Lucas from Exponent, right? And we have 2 of our faculty, Dr. Yilman Zhang, or I don't know which way. And then Sam Yao, and I also have Dr. Shinjan at the back to make sure you are all founded. All right. So you all get 5 minutes. It's the same presentation. I want you to make sure you introduce, when you're introducing yourself, say which degree you're in, whether it's civil, architecture, environmental, and which year you're in, like first to 4 or whatever you call, like freshman, sophomore, junior, senior. Right. Okay. Any questions before we get started? Oh, we got Lego prizes, so that's what you're going for, right? So, right, this is going to be our first prize for the team, and we have certificates, right? So, right. So I'll give a 2-minute warning, so you all have 5 minutes. I'll give a 2-minute before your time expires, and I've told the judges they get to ask only 2 questions, so we won't we won't be here too long. All right. So if everyone's ready, let's. One thing when you're presenting, I would prefer you stay on this side because we have a microphone and we are recording it on Zoom. So if you stay here, you can control it. I won't change the slide, so you get good things. Okay. Ready? All right. So let's see who our first lucky winner is. And before you come, you know the drill. They don't know that drill. So shout out your slide number. So make sure you have a rough idea of where your slide number is so I can navigate that quickly. And then I'll play your song, then you come over. So make sure your video is ready. Any last refresh requests so that you have your presentation? Wow, everyone's ready, so no one asked me to refresh it, but okay. All right, let's go. Oh, make sure your team name is in here. If I'm missing, let me know. Everyone's here? Found your team name? Okay, let's go spin and see who our first lucky team's going to be. All right, Bad Family. Hey. Oh wait, I now need to figure out if I can actually have audio in here. 25? 30. Okay. Let's see if I can play audio here. 35. Sorry, I can't hear you. Oh yeah. Yeah. Be next to your microphone. And then, yes, you can stand close with me. I'll stop the timer and then you are good to go.
Okay, are we good to go?
Not yet. I'm still figuring out how to set 5 minutes. Okay. All right. You are good to go.
Okay, hello. We are the Bat Family. My name is Ileana. I am the kind of organization and project definition manager, or that was my role. Oh, I am an environmental engineer. This is my second year.
I'm Kyla Rush. I'm also a second year environmental engineer, and I did a lot of the modeling and software stuff for the project.
I'm Alex. I'm first year environmental engineer, and I was responsible for research and mitigation strategies.
Yeah.
Okay, so the problem that we want to explore is when Hurricane Halong struck Kipnuk, it caused a lot of oil spillage, especially from home and vehicles such as heating home oil, cooking oil, and gasoline. So we want to model this situation and understand how fast the oil spreads and how it impacts communities to understand how we can implement certain mitigation strategies.
And then this is kind of a breakdown of how we went over creating our models. This first one, we started with the Professor Kumar gave us this game of life where it was based off of an erosion where this first beginning darker cell, it would have a probability of all the cells that touched it to either expand or distribute in that way. We continued this with importing the river near Kipnuk. And so the cells are kind of small right here, but it would stay in the barrier of the river. We kind of moved away from this as we found a model that was more relevant to oil spills. This allowed us to put factors like water current, winds, direction, and velocity, the temperature of the water, ice density, and salinity, and all of these impact how the oil is distributed. And you can see here, this is just a test model with like very North Alaska, not Kipnuk, but here, this is where we modeled it. Just an image. Those 2 points are where the oil started, and that's how it would distribute along that river. And something significant is that the NOAA model, the GNOME package, was for only coastlines, and so we had to integrate the river using the BNA file, using BNA files, and so that's a challenge that we're going to talk about as well.
So as for our model, like Ileana said, the biggest challenge that we had with making the model apply to our scenario in Kipnuk is that NOAA, which is the National Oceanic Agency, it only provides coastline data. So we could only model oil spills off of the coasts of anywhere in the world. But we wanted to apply this to a scenario inside of in the interior of Alaska with lakes and rivers. And so the biggest problem was doing BNA maps. So we had to use QGIS to export the shapefile and then convert the shapefile into a BNA format, which is like a coordinate system. And so this took a very long time, but we were able to successfully model the impact of different things like winds, current, and temperature of the water and stuff in how the oil diffuses throughout lakes. This is right near Kipnuk, and if the model works. Improvements would be to provide detailed maps across the entirety of Alaska, so not just in the Kipnuk region. But if we can provide these BNA files on a larger scale, it would allow more mitigation strategies to be implemented and more communities to use this regularly and have it available for them.
1 minute.
So some of the next steps using this model would be to implement mitigation strategies. So because it takes time for equipment to be transported to this area, we want to calculate the amount of equipment that we need, as well as the amount of area of oil that we want to contain. So that's one of the next steps to implement.
Yeah, so pretty much the next steps in our GNOME model would be using the repeated GNOME runs to update forecasts on communities in live time so that they can see when it's safe to return to their communities and start with cleanup of their communities. And also, we could use the GNOME model to identify specific places we might want to place simple protective equipment and protection strategies for water and food supplies in the community. So yeah, this is our model and what we did to make it more applicable for Alaska.
All right. Thank you. No, total two. So.
Quick question. So how is the wind speed or wind data is incorporated into the model?
So pretty much the GNOME model, which is like the Python model that we imported into VS Code, it has the wind affects like the surface distribution of the oil because the oil is often on the surface of the water. So we don't know the technicalities of how the model implements it, but we changed the wind speed and current to affect different scenarios in our model.
Yeah, there were different, and like we coded one input for velocity of the wind, and so that's purely surface, and one for the current. In the very first, and like this one, in that top one, I believe it's just an X of a west direction of wind, not current. We didn't put anything for current for that one. But we can also input two different winds, like starting points or directions.
One more.
Sure. It looks like this is mostly sort of like a reactive thing where you're figuring out what the mitigation strategies are now. How would you think about the framework? Like, how would you adapt it to be sort of a proactive, like put up barriers in these locations? Do you think that would be possible within what you've been building?
Yeah, so if we had some type of like risk points where like maybe all the oil would come, or there would be a spill that there's a risk of a spill in that point, then this could show how possibly that could spread. And we were talking about, I think we would probably want to see like a reactive, like how the mitigation strategies would work reactively, and then as we discover which ones would work, like to be able to actually simulate in our model, to be able to use, like, I think the barriers would work rather than what was the chemical kind
There's
of
chemical dispersants that you can
dispersants. But those could be shown if there's like a risk point,
Yeah.
because all of these come from, like, these start at the top.
I see. So like you kind of find the hot spots, if you will,
Yeah.
and proactively implement your mitigation in those to avoid continued issues.
Yeah, and ideally the model would simulate how that affects the dispersion of the oil and stuff. And that is a capability of the model, but we didn't get that far because we were mostly focused on being able to generate the VNA maps for the Alaskan communities.
Gotcha. Very good.
All right. Thank you. Wonderful job. Thanks for getting us started in an amazing way. All right, let's see who our second lucky team is going to be. All right, ready? Here we go. Yeah. Power pause. All right. 45. Okay. I'll like hold on. We'll play the song and then you can. This one. Okay. Oh wait. Is that an image?
Oh, I did it on.
Okay. All right, let's do this. No worries. What's your song? What is love? Okay. I'm gonna do it. Okay, hold on. I don't want to play ad. And okay, what is love? Okay, like this one. Okay, somewhere in the middle. I stay in this area. I think it should pick up. All right. So ready?
Okay.
Yeah, that's fine. I think we should be able to pick up.
Well, hello everyone. We're the Powerpuff team, and I'm Yuha Kim.
I'm Sophia Poros.
I'm Chanel Hernandez.
And I'm Sophia Alvarez. I'm a third year civil engineering student.
Oh yeah, I'm a second year civil engineer.
I'm a second year civil engineering student as well.
And I'm also a second year civil engineering student.
Okay, so our focus is on determining more efficient evacuation pathways throughout Alaska. We're looking at how to improve transportation routes and ensure that shelters are accessible when emergencies occur. Oh, we do it. Okay. So the main problem we're addressing is that people are left without safe evacuation routes when a disaster strikes. There's poor infrastructure and lack of road connectivity, and there's also minimal and hard to find information about the location of the safety shelters that do exist. And in the event of a disaster, phones and computers might not work. And actually, when we were doing research for this project, we were trying to find information on these safety shelters, and we couldn't. And we were doing this with Wi-Fi and resources, and we weren't under distress. So yeah, we are trying to make information more clear and accessible in the event of an emergency.
Okay, so when designing our program, there's 4 things we wanted to keep in mind. First, we wanted to connect our disaster zones to our shelters that we have researched. And then second, we wanted to optimize our travel time and paths by calculating the quickest evacuation paths. Third, we use this to find optimal flight paths from point A to point B and ensure that all the shelters are not beyond capacity and the evacuees are reasonably distributed between all of them. And then fourth, we wanted to determine flight logistics by determining the number of flights, travel time, and other logistical needs such as distance between the 2 points to create these evacuation flight paths.
Next.
And so the technical process behind our project was we used an event-driven simulation to build a website that takes into account the distance from the cities and the shelters and the capacity of each shelter. So first we found the location of each shelter and calculated the distance, and then we found the maximum capacity. And our approach to dispersing the evacuees was first based on the distance. Obviously, we wanted to maximize like the closest location first, which was at Bethel. And afterwards, we would just evenly distribute the rest of the evacuees towards the further Anchorage locations. And our website also has a slider that you can adjust since there's also changing like populations that we can account for. And we had to change our approach because our first approach, we used open streets, which relied on more like developed areas. And since our areas weren't developed, there were no pathways that we could discover. And so we couldn't like pinpoint where the locations of the shelters were on the map. And so instead of finding like pathways on the floor, we decided to switch to like direct flight paths instead.
So as for our deliverables, as you can see here, we have a website design. It's framed as an interactive map, as in you can zoom in, you can click these little points of interest. So the greenhouses represent the shelters. And when you click it, you can see all the information, the evacuees allocated, the capacity, and what percent of the shelter is utilized. And as you can see here, it displays all kinds of information, including the logistics for the flight paths that we'll have to create to evacuate these locations, and all the information displayed here. So one issue that we ran into was that, as you can see here, these 2 shelters are very, very close to each other. And before we had a very static map, it was just very hard to see. So we decided to create an interactive map, which can zoom in, close, see information, close it off, see more information, so it'd be easier to see. And what we hope to get out of this project is to increase transparency and communication with these more rural areas where there's less information available. And yeah.
Thank you.
For Alaska, what to envision and which central location, for example,
That's something we want to look more into. As of right now, I forgot to mention this, but you can add origins. So the shelters are fixed, so this is just for within Alaska, but you can change the locations of like where you need to evacuate from. So that's more fluid, but in the future, we can plan to implement this to other areas. But as of right now, it's fixed on these 3 shelters that are in Alaska.
Sure.
Oh, I was just wondering, would it be useful since there's 2 shelters within Anchorage to have, after the flight, like ground transportation to those shelters from the airport? Is that something that could be integrated that would be useful?
Yeah, that's something we also limited. One of the limiting factors is how to get to these airports or like these runaways. So that wasn't within our scope of the project.
Last question.
I know y'all had extremely limited time to develop this, but any thoughts on what if the internet goes down? What's your plan to be?
Yeah, that was an issue. So
Be-
we're hoping this is more of a proactive thing. So this will be posted before the internet.
The
will go out.
offline information
Yeah,
that you
so-
would provide to everybody.
Yeah, this works
Yeah.
well because it can be proactive and it can be before the disaster and after the disaster. Got it.
Thank you. Hey. All right, let's go. Great job, Power Pops. And let's spin it. And the Mies. All right. There's also a slide switcher or laser pointer if you want to use one. I remember to introduce which song. Yes, good point. Waiting. Slide number.
Oh, 29.
29. Right. Oh, wait. I haven't started your timer yet. Hey, you're good.
Hi everybody, we're the Mies. My name is Jean Packlip. I'm a second-year civil engineering student.
I'm Lucas Ruda, and I'm a second-year environmental engineering student.
I'm from Sean. I'm a PC major, I'm a freshman.
Okay, so in Alaska, the main mode of transportation between cities is by aircraft only. So helicopters and planes are the main mode of transportation. And because of this, there are restrictions such as weight and volume. In Alaska, because of the Alaskan typhoons, the shelters need aid and materials such as like water, food, medicine, blankets, etc. And these are transported using aircrafts. It is seen that 30 to 50% of volume is wasted globally in aircrafts. This means that many people can't receive the maximum amount of aid that they need in these shelters. In addition, because there is no streamlined process for these items to be delivered to shelters, this causes a 24 to 48-hour delay in which these shelters can receive these aid items. In addition, because of the lack of optimization in these aircrafts, it causes waste of fuel, waste of money, waste of efficiency in general. So we created a website that Andre can elaborate on.
Yeah, so we created a website called AirStack. So it's a web app using Python and HTML to run its core functions. It uses Python to run its backend API system and HTML for its frontend. And we have 2 kind of views, the loader view and the admin view. The admin view kind of allows you to add items into the system. It generates, based on its algorithm, a layout, how to actually package these aid items into the aircraft. And then it generates data based on it. So putting a weight distribution of an aircraft, it creates a open SCAD model, which allows you to visualize it and see it. And then the loader view allows you to see exactly how to fit these 8 items into the aircraft effectively. So it has all this functionality built into one web app.
So right here, you can see a demonstration of AirStack. Right now, you're looking at the administrator view, where you can input the type of supply you need, the amount of the supply that you need, and the priority of using that supply compared to other ones. Then you can generate the layout, which is going to be an open source CAD file, as well as a PDF file that the loading crew can look at. So right here, this is what the loading crew is going to see. And if you scan that QR code with your phone, you can actually see the loading crew layout on your own phone of what's being displayed here. Right here is the open source CAD model, where you can have a more detailed visualization of the even weight distribution of all boxes.
Students.
So now that we've developed AirStack and we can solve the problems for maximizing the space of helicopters, as well as reducing the time it takes to get supplies to places that are in need, we can start with the deployment process if they want to use AirStack. So we can start by creating a contract with Alaska Homeland Security, or maybe the Tribal Emergency Response Organizations or the National Guard. And then all we need to do is set up a permanent server for AirStack and then set up the infrastructure for the security of their login information for the administrators, and then also the loading crew. And then once we've done that, AirStack is ready to deploy. And here are our sources. Thank you.
Go back to the video so y'all can like look at the website and QR code.
All right, got still 1 more minute to play.
Okay. Wait. We can play the video again?
Yeah.
Okay, sure. Good. Wait, you can't see it because it's in 2 times speed, but there's also like a drop-down list of different like things. The quantity and priority are obviously like some important things that is accounted for whenever loading these aircrafts.
And then for now, just for like simplicity's sake, we're just keeping the aircraft specs locked and we're just using the UH Blackhawk. But in reality, there would be different aircrafts available with different dimensions and constraints.
Yes. Oh, and we just decided on a semi-cylindrical like area for the UH Blackhawk.
Because the bottom can be like for fuel or other things like that.
Hey, great, thank you. Question.
Gene, can you go back to what first or second slide, get the percentage, like the underutilization of, 30-50% volume wasted globally? Did y'all estimate how you might reduce that waste with this?
Wait, the waste is reduced because we're optimizing like the amount of objects that can go inside the aircraft. Like
Okay, so your goal is
to
no wasted volume.
Well, minimized waste.
Okay.
That's our goal.
Yeah, so that way people can like input as many supplies as they can, and then any like extra supplies that aren't going to fit within like the maximum weight allowed, they're just going to be excluded from
And then you
the
already factored that in
Yep.
with the payload of a Black Hawk and.
In the website, it shows like the maximum weight, the dimensions of the Black Hawk, and everything. Wait, sorry, again.
Wait.
Yeah. Will you consider the trade-off between how much more volume you get, however, how much more battlefield you need to fire from?
It's most okay.
Yeah, I think we saw a little bit about that in our research, but that isn't something we included. But that would definitely be good for us to include like in future development or when we're actually implementing it. Yeah.
Louder.
In what way are you the test file that you're showing better than current pages?
Oh, like how is it optimizing it better?
Yeah.
Yeah, so the main thing that it's doing is we have a little bit of like a margin of error, so there's a little bit of space in between them. But in practice, it's going to make it so it lays out all of the boxes. And the main thing that it's doing is it's making the weight distribution even, so there isn't any imbalances. And then what it's also doing is fitting all the boxes into the space with like, because all of them have different sizes and weights and things like that. So it's fitting them all into the space, so you can fit a lot more of them because it almost fits them together like a puzzle.
And in addition, the example that we used, because we used 100 blankets, we don't have variation in volume and weight. But if we were to do, like, for example, 50 blankets and 50 toolkits and 20 like first aid kits, it will show like how it incorporates, like you can see the different sizes in like OpenSCAD, and then you will see like how it incorporates in the weight distribution.
Nice. Thank you.
Thank you.
Hey, hi. E. Pokemon. Like, hi. Right? They all get the same time. So. What? I can refresh it. That's like I'll just refresh. Become like go with what you have. Like, okay. All right.
Hello everyone, we are Team Pokemon. I'm Yagni Trivedi. I'm a grad student pursuing Masters in Construction Management.
I am Pujan Pasavala. I am also pursuing my Masters in Construction Management.
I'm Jugal Shah. I'm also doing Masters in Construction Management.
I'm Rishabh. I'm doing Masters in Computer Science.
We started researching about the current challenges faced by Alaska, and the one thing we identified was the disaster logistics lacked a centralized, visible platform wherein all the stakeholders can come together and try to identify what resources are needed and when. The current model is a reactive based model because after the disaster strikes, the actions take place and it requires a lot of initial damage assessment and resource allocation, identification for it to be distributed to the places that are in need. What we are trying to propose is a decision tree predictive model wherein the core is to collect data from historical resource distribution information, user input data, and weather forecasting. After the first step, it will all come together to integrate the provided information, and the final output would be a place where the model can predict and analyze before any natural calamity is gonna strike, and they can identify what are the resources based upon the type of disaster, and it can try to identify the most efficient route. This can lead to mitigating cost overruns, and the most important thing is they bring all the stakeholders involved into one platform.
So, okay. So I think there's been issue. Sorry. So the step one was, the step one is data collection. So here we are using a traditional method to collect the data through a React Native based web app. So here there is an admin dashboard and a user based dashboard for the Alaskan people. So as an admin dashboard, you can create the hotspots and create the inventory for the people. And the people, as you can see, the user, they can pick the nearest the hotspots and get their inventories. So that's how they get to request the inventories to the admins and they get to approve. So this is how it's working. And as a next step is data analysis and prediction. So for the data analysis, we are for the data analysis. Okay, so this is how it's look at. These are the users and these are the hotspots. So as you can see, these are the users, these are the hotspots, and you can see everything. So, and for the prediction, we are based on the input, disaster type, inventory, and resources. We are predicted the quantity needed.
So the step 3 will be the optimization of the goods that is being requested, and so basically the battle is a main hub from where the goods will be transported to the smaller villages in Alaska, and we try to optimize our plane routes with the help of 5 constraint, that is node constraint. Node is basically the airports on which the plane will land, and how is the current situation of that airstrip. A set constraint, that is the planes that we are using. It will be like more a plane with larger capacity or a smaller capacity. Human constraint, for example, the pilots are not available, and the FAA rules for pilots to fly at a certain hours. Then environmental constraints like the snowfall and so on, and the demand constraint. For example, food and medical supplies are the most urgent, and we try to establish this constraint and made this simulation on which plane to use and where to go with that plane.
Now talking about path to deployment. So we have considered 3 phases for that. The first phase would be the data foundations and partnerships with the local government and all the different stakeholders. Then we'll be focusing on the prototyping of the model, in which we will be working on data integration and machine learning model, which will help us scale our logistics as well as become efficient. And at the end, we'll be focusing on the helping local communities to understand the our dashboards and network, and the impact that we are focusing on our response time, increased efficiency, accountability, and bringing local communities together. Thank you.
To handle different types of disasters. How is that incorporated into the model? So to incorporate disasters, basically we are using the decision tree classifier. So here we are dividing based on the type of disasters as like for the hurricane, the tornado, and earthquakes, and based on those input points, we are sorry. We are making the model, and so that it can predict the values, like what are the what are the needed value, like the shortages, what are the predicted shortages. So that's how we are doing this.
I see, like a hurricane is going to have more requirement for this material.
Yeah.
So it will be like trained on the past data that is already available, plus the data that we are collecting from the users, the person who request, like we need this food, this medicine on day-to-day basis. So there is like we can predict what will be the 1 week requirement for food and other supplies. When so even if there is no hurricane, and if there is hurricane, the food supplies almost will remain equal. So we can like predict what will be the actual requirement, because in certain cases there are chances that people might hoard the foods in hurricane or like disasters. So because the transportation is with the plane, we can like optimize what we need to actually transport to the communities.
So every disaster could be different. Right? If you use the historical data to do the prediction, the results may be totally wrong. So how the model can adjust
So to adjust the predictions, as we are using a dashboard, so we are taking the real-time inputs also based on the what are the requirements for the user, and also we would be incorporating a feedback loop mechanism also, so that the model can like be more better and it can be more resilient, like what are the food and like inventories are needed.
Okay, thank you so much. Hey, all right, let's go. And again. The second theme. All right. They're easy to find. Okay. Okay. We also have this. Yeah, please. This goes forward. Yeah, bigger one goes forward. Perfect. Here. All right, hold on. Let me stop the timer. Tell me when. Okay, my name is Evan Segura. I'm a second-year environmental engineering major. This is.
I'm Jonathan Waitaka. I'm also a second-year environmental engineering major.
I'm Sophia Trin. I am also a second-year environmental engineering major.
And Kaina is also a second-year environmental engineering major, but she's sick. But she did help out a lot with this project. And what we did was Western Alaskan erosion modeling. And why is that important? Or as Shakespeare said, where's the rub? Okay, let's go to the next one.
So yeah, what?
So,
Sure. Yeah. What is?
so we can see the slide. Yeah.
Yeah. So within Western Alaska, erosion is constantly damaging key infrastructure, and as a result, is threatening emergency response. Sorry. Yes. In recent years, this region of Alaska has actually been experiencing harsh and intense, a notable increase in harsh and intense weather conditions, as we can see, like the recent Tiger Bang, and this leaves these coastal communities devastated and sometimes isolated when some of their few roads are destroyed. So the communities we're going to be analyzing are Kotzebue and Kunigok. Right here, we're looking at Kotzebue. This large area is their lagoon where most of the erosion is actually occurring. Because on the seawall, along the coast, they've implemented a seawall that prevents ocean erosion. And right here, we're going to take a closer look. This is Stevens Way Bridge,
yeah,
which is Kotzebue's one of two evacuation points. And since you can see its location is actually on the lagoon, and due to the erosion, the foundation of this bridge is going to soon make it not a viable evacuation, which is very scary. Additionally, we have Quinnigock, where they're currently implementing sea bags as a preventative measure, but we're going to look at right here their waste lagoon, where they're also experiencing similar issues in Kotzebue, where their pipes are being displaced due to the erosion, the pipes are being exposed to the freezing temperatures, and they're bursting as a result.
Additionally, we can see that their wastewater lagoons pretty close to the ocean, and we don't want the waste going into the ocean. So what do? Here's our model and how it flows. First of all, you go into Google Earth Engine, my good old friend, and collect some TIF files that you then put into ArcGIS and collect some relevant contour maps of your community. Then you input that base path that you just saved to your files into our little data prep IPYMB, which then produces a water mask, which identifies, hey, here's water over here, there's land over here, includes current weather API data to help forecast extreme weather events such as Typhoon Hailong, and elevation data to help make erosion predictions. Our image segmentation file confirms that the water mask is accurate, and then all this data gets input into an erosion probability function that is then put into the prediction model that makes future images of our erosion event. But this is way easier to see when you can visualize it. So first, this is what the image segmentation model produces. You can see the NDWI, which is how you identify what's water, what's not. And you can see the water mask, and it's a little better when you color it properly. There is a little bit of an issue with the TIF because it's not perfectly rectangular. However, there is some significance in the model because it does, in fact, produce erosion. As you can see over the years, the yellow part is land. It
it becomes eroded in the coastline. And this is incredibly significant in our communities because
Yeah, so the significance of our model involves being able to target these vulnerable areas that have been highlighted, as well as being able to notice potential vulnerabilities in areas that have gone unnoticed. With our model, you can also add protection measures and simulate how the erosion will then be affected. And we hope that in the hands of the local governments of these communities, they'll be able to design future preventions for their public infrastructure and residential areas.
so there are some problems with our model, including, Jonathan, that's you.
Oh, yep. So our issues, there's some problems with the image segmentation and identifying water, as well as identifying shorelines. And then our erosion probability, just the data, being able to find that online was difficult. So there might be problems with adjusting those numbers to be exact. And then in the future, we hope that we'll be able to train a CNN model with multiple TIFs to evaluate the water masking and improve the quality of our images. And we hope to be able to implement the effects of erosion by permafrost on the seawalls and shorelines as well.
That is the second team, and feel free to ask us any questions. Any?
If you go back to the color.
Yeah.
How do I read this? Like in year 9, what would you identify as, hey, you really need to focus on this area? Is the yellow in that? Or
So the yellow brightens, this dark yellow represents it's just land, right? As the yellow gets lighter and turns into a green, it gets more eroded. And then eventually the dark blue is what represents the water.
So the darker the green in year 9, those are where we need to focus.
Yes, exactly.
Okay.
And you can see how we need a CNN model right here because if we go back, you can see how this is what it should look like, and since it's taken at an angle, it interprets it as land, which is an issue. Yeah. So, any other? Yeah, shoot. Sure.
Were y'all able to, or would this be helpful to talk about protection strategies? But would it be useful to model how the erosion was different for different materials, like for the Stevens Bridge? Like, could you isolate that while also looking at the land erosion?
Well, we hope to simulate other infrastructure things like, say, a levee or maybe even a seawall right here with this wastewater lagoon to prevent the erosion. But and that would in turn decrease the function of erosion probability, and that's the way we would model it.
Yeah.
Do you think that segment would build up in some other place that should be modeled, or would that maybe not be useful?
Well, currently we'd have to implement that overlay the elevation data, which was a struggle because this was all coordinate based and the elevation data was not coordinate based. So,
yeah. All right, thank you. Great job. All right, we're halfway through. Okay. Jingle bells. All right, slide number 14.
Yeah.
Okay. They're not rated on their music. You got a pointer? Yeah. This is forward, this is back, and there's a laser pointer. I'll go start the timer, okay? And make sure you tell which you. Right, ready? Okay.
Hello, we are
The Jingle Bells.
I'm Sophia Terwilliger. I'm a second year architectural engineering major.
I'm Anushka Conturla. I'm a second year informatics major.
And I'm Elisa Beekman. I am a second year environmental engineering major. So what we're going to do in this presentation is we're going to first go over the problem and why that's super significant. Then we'll go over our idea for that. Then we'll go over the computing and the modeling for that we did for it. And then lastly, we'll talk about our issues that we had, and then we'll go over the future implementations and innovations that we had for this.
Okay, so our problem is permafrost in Alaska. Right now, 80 to 85% of Alaska's soil is compromised of permafrost. And what is that? That's not just ice, it's soil, water, sand, and that's all cemented together by ice. And like ice, as we know, it thaws, and this creates density and volume changes, which is through a process called thermokarst. And this causes structures to collapse, and it's just an uneven foundation for buildings to stand on.
Yes, so our idea is sort of along the lines of a self-stabilizing structure, and we took a lot of inspiration from buoys that are implemented on oceans and a bobo doll, if you know what that is, where essentially there's just one stable equilibrium point and everything else is going to force it to try to get back to that stable equilibrium point. Another structure that we took a lot of inspiration from is called the gombak. Same situation as with buoys, but everything will try to get back to the stable equilibrium point. So what we did to try to try to simulate whether this would be a good idea or not would be was using a wobble model simulation. So what we have here is a constraint of a uneven ground. So you can see that it like wobbles to a stable point at the divot. So and then the next constraint that we did was to see if a point mass would impact the wobble too much, and also again, it does reach a stable equilibrium and it does still stay upright, so that gives a lot of hope. And then the last thing we did was a stability comparison between different types of structures with different constraints, and just to see how that would impact how upright it stayed or whether it would like continue to be stable.
And we use Matplotlib. I just want to give a huge shout out to our mentors and Dr. Kumar, because they did help us code a lot of this. We are novices in this, but they just help a lot with that.
And AI, that was great.
Yeah, so coding wise, we forgot to save in the beginning and we lost around 40% of our progress. And when constructing the sim, we also had a lot of issues with the domes warping, and this was caused by a projection error. And in the future, when implementing this, if used for housing, a main problem we would have to figure out is how to keep the house from moving and shifting around in space. And multiple large masses shifting around the house might also cause it to wobble. And a lot of consideration would also be need to take in with the materials to combat things like mold. And we would also need to figure out how to make the houses modular so they're more easy to build.
Okay, so why is this the solution to our problem? Right now, as I said, climate change, there is a freeze-thaw cycle. So it's not just frozen and it's not just in a wobbly jello state, it changes. And we want a structure that can self-stabilize, because right now the Alaskan residents do not have security in the longevity of their houses. And especially with the typhoon, this is a unique situation where we can start from the ground up, because a lot of homes were destroyed, unfortunately. We also thought of other ways that things can self-stabilize. We were just brainstorming such as a beanbag foundation. So that would be, the beams would ideally be like a lower density than the permafrost. So they would be like causing like somewhat of like a buoyant force up. And if there were density and sinkhole problems, then ideally there would be some like coverage to keep the foundation more level.
Yes, and if we were to stick with the dome-like structure, oops. Another whoopsie-doo, okay.
I can just.
Yeah, so it's still good. Okay, there we go. Yeah, perfect. Okay, if we were to stick with the dome-like structure, just to combat the freeze-thaw cycles that are very prevalent with permafrost, we could add maybe some origami folds to the dome. This could also help with modularity and implementation of the dome foundation. But ideally with the origami, it could like expand and contract with the freeze-thaw cycles. And then the last consideration that we brainstorming idea that we had would be a new heating system, because as we are redefining essentially what houses look like in Alaska, we would also need to redefine how the heating heating works for these houses. So we took inspiration from a Korean ondol floor heating system, where instead of having heat go from the ceiling, or like heating go through pipes and down through the house. They instead have it go through a permeable flooring where air just gets pumped in through, and then you have the entire house basically heated from the ground up. And if you have any more questions, please let us know. We enjoyed this topic very much. Yeah, we didn't exactly get enough time to consider this fully, but it would have to be entirely dependent on the material that we use, and that was also a big point of struggle as to how we could possibly do something that like actually moves with the permafrost. It's just up in the air. It would be perfect if we could. It's just we have no idea how.
Food for thought.
Food for thought, yes.
She has research on this.
Yeah, Dr. Kumar pointed me to you, so I know a lot of what you do.
Any other questions?
I know y'all said that it's a freezing thaw and the entire structure could shift. Y'all think at all about I don't know, putting up some sort of bollards or something
I'm sorry, what? Putting up what?
like in the water. It's some sort of, think of it like
a boathouse?
No, just something like a column that would sort of contain.
Well, the
You'll give
problem
me thought to
is
that.
like the density is completely different in different structures. So it's more like a jello-y, like quicksand like substance. So like it goes down.
But you could do a drill shaft that would go beneath that.
Yeah, but how far do you have to go?
Yeah.
Well, that's y'all.
Yeah.
I think one
Like-
thing could be like,
a geotech.
Yeah.
like you could barricade it so that it doesn't like.
That's kind of what I'm getting.
Okay.
It's like even if the barriers are moving up or down, it still retains it within their house fenced area.
We could do that, but these communities, we're not exactly, we want to make it so that the structure is what we're focusing more on. The ground is not stable, and I don't know how well affecting like changes in the density does that is like an effect. But it is like a good idea by keeping the structure stable, but
Also, the permafrost is like that. The permafrost issue, just in general, is just so uncertain that if we were to like go into the ground, we don't know how much that would impact the actual ground itself. Yes, it's a good idea.
Right, y'all didn't research like under the permafrost. How far would you have to go?
No, we have no idea. Yeah.
Fair enough.
there's always no on the housing.
Yes.
Right. Thank you. All right, spin the wheel time. For red. Okay. Architecture. All right. Slide number 19. Okay. Oh, you're literally next one. Nice. Ready when you are.
Hi, everybody. Welcome to our presentation. This is Team Hackatecture. I'm Egan. I'm a sophomore architectural engineer.
My name is Gabriel. I'm a civil engineering major in my third year. I'm a first year's master's in structures and land institute, and our teammate Momoka could not be here with us.
So we decided to ask the question, can we use AI and aerial imagery to identify buildings and assess structural integrity?
As is obvious by now, a lot of us are working with the recent typhoon in Alaska, and right now it's sort of decimated the rural villages. And we want to see what we can use to help out. And one of the things that we know after disaster, a lot of helicopters can fly over and take a lot of aerial imagery. And so we thought, what if we could use imagery to assess buildings, whether they're damaged and how bad it is, and what materials are missing and what materials are needed. So we had to train our model, and after looking through a bunch of data sets, we used images from the job instrument of 2011. And that was a nice data set because not only were there a lot of high quality images, but also each image had text attached to it, which classified as damaged, partially damaged, totally damaged, as well as the building's location in the picture. And we fine-tuned two models to develop our own model. We used the mobile NetB2 model for classification, and we fine-tuned the YOLO model for image segmentation. Segmentation basically identifies what is a building and what isn't a building. We didn't want to analyze grass or roads, but just one buildings. And we want to classify, like we said, based on how bad it was. And with the YOLO model, we had several choices. We could use small, nano, or medium, but we used the medium model because in a disaster like this, we felt like it was important to be more accurate, even if it was more computationally expensive, and we hoped that the government would help with the finances of running those models.
Okay, so for our final app, we combined both of our AI models that we trained. We have the precision and recall numbers for both of those. Precision is the accuracy of your positive IDs, and recall is the accuracy of your negative IDs. At the bottom left, we have the accuracy increasing with the number of epochs that we did, the number of iterations for our training. And then we used a simple UI where you can upload a photo to a web-based application. And so what we have is an example on the right where we uploaded the photo on the top, and the photo on the bottom is what our AI returned. So in the green, we have untouched structures. In the cyan, we have damaged. And in the dark blue, we have collapsed, along with a confidence level that the AI feels it has. And then highlighted in red is the incorrect instances. So I think it's fairly accurate for the resources that we had.
All right, so looking forward, we feel that this will be a helpful tool, primarily for humanitarian work in impacted areas after natural disasters. Some improvements that we thought about was using, first of all, a larger data set, which would then be used to do more model training for AI. Then we could also have a better GUI and also the ability to analyze multiple images simultaneously. And moving on, some things we thought about adding to our model expansion, but didn't have time enough for it, was first of all, segmentation of damaged object materials. Kind of like this was something we thought about. So it would show metal sheets and concrete and identify those materials for it. We also thought about doing an estimate cost of material and transportation for it. And then lastly, do a GIS map of the damaged buildings so you can better see and understand the situation of it. And the potential impact of this tool would be to rapidly assess damage and natural disasters, also to optimize the resource allocation and the responder safety. We also want to thank Professor Kumar and the mentors for helping us with the programming code and so. And yeah, any questions? Thank you. Oh, it's a before and after. Yeah, so this is the input image, and this is what we get out.
I can hear you.
Yeah. Yeah. So the purple highlight is the areas that it got incorrect. And it is a lot more in the untouched category. And I think that's just the way that our model decided to be. You can see in the image that the buildings are almost even not there at all. So I think it just happens to be the northern part in this photo. I think it's just less accurate in identifying buildings that have been completely destroyed, because it's hard to recognize the building in the first place.
No, they have only one image.
This is only off.
They only have after image. You go back one slide. Did they say that these are? Oh, because you say in the text here, these are aerial images of before and after the disaster.
Yeah,
Do
so
you have before
the data set we used was before and after images of Joplin tornado. So
I think the issue is the data set was so large and it took such a big amount of time if we were to train the model for it. So we just like sampled 10% of the data. So I think the model just trained for a few photos just after the disaster and not the whole data set for it, before and after photos.
If they had more time. Okay.
Yeah.
Oh. Yeah, we could do like before and after and then look at accuracy, you know. But yeah, also their training time was a lot. So it was like given day and a half. So I think that was a lot of effort. Thanks. Any other questions?
Tornado damage is quite different from, say, earthquake damage, wildfire damage. How do you think the model could be extended to look at other types of natural disasters?
we would just have to train the model on using images from different natural disasters. The data set that we used had, I don't know, 12 different natural disasters or something, and we just trained it on the Joplin tornado. So we would just expand our training data set.
All right. Thank you. Thanks, Christian. Hey, all right. We're getting to the final four. And wild trackers. All right. Slide number 50. Wild trackers. Okay. I've been having fun for the last few days. I will go set the timer and then you can start. Thank you. And remember to say which year.
Okay.
There you go. Hey, you're good.
Okay, we are the wild trackers, and we did an animal tracking map for the disaster in Alaska.
My name is Stella. I'm a second year civil engineering student.
My name is Marissa, and I'm also a second year civil engineering student.
My name is Anya, and I'm a third year environmental engineering student.
And I'm Laura, also a sophomore school engineering student.
Okay, our focus was on animal tracking and reconnecting owners and their pets after the disaster in Alaska. The new typhoon separated a bunch of animals and their owners. And we aim to do a community-driven like software where community members could upload pictures of lost pets, and also people who found animals could upload their pictures. So we did an AI matching software to see, like, narrow down people's pets and reunite them quicker.
So basically our approach can be divided into three different sections, starting with just the baseline. We kind of had the idea of building a year-round database where we're letting the community members upload photos of stray or roaming animals in their area, so we can kind of get an idea of the population patterns around there. For the second part, the registration, that's more for personal pets, and residents can upload photos and specific information detailing like a profile for the pet so that can go into the system. And then finally for the matching, the AI that we worked on is basically analyzing those new uploaded photos of found animals, and that would be analyzed against the database so that we can identify potential matches, which is leveraging the missing pet new uploads and what information you're.
Okay, so basically we trained our ML model to have we have this database of just animals that we found on Facebook in Bethel. So that's like in Alaska. We focused on like that problem. And then the users would upload their personal image in this like one area. So they upload their dog per se, and that image was like the features were extracted to see how that dog matched with like all the other like ones already in the database. We ran into a couple problems with this at the beginning, just like extracting like the background of the image and like not necessarily the dog, but we like fine tuned our like model to kind of focus more on like the dog's color, features with like the collar and like the size of the dog. And then basically the similarity was like calculated to find the top matches, and then our output is the top 3 dogs that were the most.
So this is the real world implementation. So this is an example of our model running. So this is the photo that we uploaded as if we were the owner. And these are the photos that pulled from our database. Obviously, this is the same photo. We just did that to prove that it worked. It's the most similar image, obviously. And then this is the same dog, just a different angle. And it's the second most similar. And then this is the third image. It's a different dog that has similar characteristics. So this just proves that you can help narrow down the options. Say that there was like 500 photos in the database, you can narrow it down to a smaller number, so you wouldn't have to go through as many to try and find your dog. And we had 3 different like perks of this model. So by pre-registering your pets and sending in the pictures of like strays, you can speed up the reunion, and emergency personnel could be given that information to help rescue them quicker. And this AI matching also helps direct our resources more efficiently and eliminates people from just like blindly searching for their animals. And finally, this year-round data helps improve long-term rescue and helps increase support for domestic animals. We also wanted to hopefully use this for other disasters in the future, and it could also be used when there's not a disaster or if someone has just lost a dog. So that's pretty much all we have. Thank you. If you guys have any questions, let us know.
The easy one. Does it work for cats?
Yeah, so we just focused our database on dogs, but it can be used for any animal. Just depends on how many photos you have from that population.
Like in the 10th grade that we had, we decided just I'm also scared of cats.
Hey, third question. Yes.
Did y'all monitor the accuracy? Like, do you have any stats on the accuracy of the model? Like, so basically the image, you can also talk more on this, but like the image, we got like a number that showed the similarity. So like when it showed the first photo output, and when it oh yeah, well like it gave us like a 1 because it was like exactly the same photo, and then over there it was like a 0.7. So like obviously like you know we learned stats, but like the number it gives you a number based on similarity, and the only thing that we realized kind of like changed the numbers that we were getting is that it was taking the background, which is something that we need like in the future, that would be something we have to focus on, because the different backgrounds would make the similarity like way lower, even if it was the same symbol. So, but we did get numbers.
Great. You got a question?
Sorry to interrupt you. Yeah, just a quick question. If you think about like in addition to images, try to do some text information.
Yes, we actually, so initially we were going to do like an image to caption. We went on like GitHub, we were looking for like open sources, because image to caption is something that we also talked to Priyanshu about, but it ended up, we weren't able to work with that, and ended up getting a little bit more complicated, but basically long term, one thing that we would have wanted to add was when we're making the profiles, like we can have like a drop down menu for the breed, for the weight and all that, and those words can also be used. Once you find a dog, you can also fill out those same options, and then that can also have more space there for data.
Okay. All right. Thank you. All right, we're getting to the final three. All right. Oh, all right, three.
One more time.
Next one, back later. Let me go start your timer and then you're good.
Dr. Penwas, would you confirm maybe
Sure, we should be able to pick up.
Okay, awesome. Thank you guys all for joining us today. We're EB3. My name is Andy. I'm a second year EBE.
My name is Samir, and I'm also a second year EBE student. And then Ion isn't with us today. So this is the problem. I'm sure most of you live in Texas. In 2021, I'm sure all of us were affected by the freeze. And all of us, have at one point cursed out or caught in the grid just for not being able to sort of support ourselves in these disaster events. So our question is, how can we use machine learning to aid grid stability through aggregated distributed energy resources and simulation? And then how we're going to approach that is by using a decentralized community energy network where households communicate with each other instead of using a very centralized grid. And they use these energy resources with each other in like a market.
Yeah, and also before we jump in, we wanted to clarify that our scope was not necessarily just for Alaska. We actually wanted to make this scope wider for all of America. And for this specific project, we just chose the place that we're both from. We're both from Sugar Land, Texas, or he's from Houston. I'm from Sugar Land, Texas. We ended up using a zip code and the data set specifically from that region just to tighten up the model and also make it not super, super large so our computers would freak out. Awesome. So just going into some backend design, we both began by coding into Python. And we built a platform of a weather model using machine learning. We use XGBoost. There's a little figure on the side called figure 1. That's a little bit section of our precision tree. Just because it's super massive, we don't want to overcomplicate it and just show a little part of it. We utilize a data set from NOAA using the last 15 years of data from the specific zip code I talked about, 77479 Sugar Land. And then we took that data, cleaned it, and ended up using a bunch of different inputs and outputs, some like temperature, time of day, humidity, wind speed, cloud cover, solar radiance, all of those combined together, and we ended up working our first model. Figure 2 is the sample output. This is one of our first prototypes, but it actually improves a lot, as Samir will show in the later slides. And then expanding vertically, we ended up trying to go just straight up from our weather model. So production, consumption, equations, and simulations all were built off of what originally was in that Python file, just to not overcomplicate things and just provide a simple proof of concepts. With weather, we then randomized specific variables, and we attributed it production consumption using randomization. We use something called stochastic Monte Carlos. Sounds super complicated and a bunch of buzzwords, but it's actually just a function used to simulate tons of different theories and also add a little bit of randomness and correlations in order to just show a bunch of different outcomes to essentially basically stress test the system.
Yeah, so like Andy was saying, we use Monte Carlo simulation because we wanted to basically have a bunch of different runs of the simulation, but in each specific scenario, they call them scenarios, you have all of these different variables and they're randomized. So scenario 1 and scenario 2 could have complete opposite variables, but the point was to get as many scenarios run as possible, and then from there to kind of extract your conclusion and say, okay, from this range for this variable, the success rate goes up by X amount. So for all of our variables here, here are most of our variables. There's things like the ramp rate, which is basically how well your system accounts for fluctuations and swings. And then there's the feeder limit, which is how much your power lines and your substations can hold at a time. And then we have a correlation matrix, and that sort of shows, there's the failures in the far right. I hope you can see that there's a failure bin. And then everywhere else you see a variable type. So you can see kind of what is the contribution of each variable to a failure or to a success. And we ran 100 scenarios. And with each scenario has 100 homes with these randomized variables. You know, one home could have solar, one home could have an EV, and so there's 100 homes with the different variables. And then we came out with 5 successes out of 100, which doesn't sound great, but honestly, we were kind of pleased to see that because it shows that it's realistic. I mean, something like this is really far out. So to get 5 successes with these many variables, I think is kind of what we wanted to prove. Some image down here, some graphs here show photovoltaic is PV for reference. So the solar versus homes, you can sort of tell immediately that beyond like 400 to 800 number of homes, the model basically fails, and there's just too many homes. And I guess the market, the supply and the demand gets too crazy, which contributes to ramp, which is the swings, and then the ramp shuts down and the system fails. And then here, Andy will talk about the synthetic weather model.
Yeah, so going about our data sets, I know we specifically used 77479, which is a specific location in Houston originally, but going on and looking into the future, one of the big things we wanted to do is actually cover a wider scope. For example, for the typhoon in Alaska, we wanted to apply to a thing where the weather and the climate is super different, where the humidity is different, solar radiance is different. We wanted to be able to simulate that too. So that's just looks super messy, about 20 simulations using the Monte Carlos we were just talking about, just to cover a wider base moving forward, and it's not too messy.
All right, so just to conclude, our findings were basically, I talked a lot about this in the previous slide, but that ramp ended up being the most important variable to either signal success or failure, and that actually solar and EV by themselves didn't signal much at all. It's only when they're combined and you talk about the fluctuations that the model starts to break down. So the key takeaway is that communities are really dependent on fluctuations rather than total load or volume.
Yeah, and I'll speed it up real quick because I know we're out of time. A bunch of different risks, super high upfront costs, and a lot of regulatory compliance, and also natural disaster stress is one of the big things we want to talk about, especially talking about the winter freeze or typhoons that are affecting Alaska. And then for next steps, another big thing that we wanted to implement was blockchain in the future. Whether it's like encrypting or autonomously charging and discharging batteries is a very, very prototype idea, but it's another cool thing we think we can implement in the future. And then immediate next steps we think is in the immediate future is just exploring candidate communities to begin rolling out hybrid things. So not necessarily just completely going off the grid of ERCOT, but using ERCOT, but also testing and stress testing and see if it's even feasible to go on a situation where they can begin communicating with each other and trading energy.
Pilot program.
Yeah. And thank you so much. And we're happy to answer any questions.
Great.
This limit is 800 homes or so. Did y'all look into or do any calculations on the maximum practical distance between the homes in terms of voltage drop? Because if you're sharing 120 volts, I'm sure y'all know that can only go maybe a few houses away from you before you might go below what can practically be used.
Yeah, so the model pretty much assumes that it's a neighborhood where each home is next to one another, and it also assumes that each home has a battery. And so if each home has a battery, you can your home might be used as like the final destination, or it could just be used as like a step on a long destination between, the furthest house in the neighborhood to the next furthest house. It's sort of like each house is like a stepping stone, basically.
Okay.
And it refreshes at each battery to sort of like keep it going. It's self-sustaining.
Okay.
Other questions? What do you want to do with blockchain?
So, sort of far-fetched, but our idea was in the case that everyone has a battery, they're able to communicate with each other, right? And it'd be completely autonomous. So in the sense of when people are actually giving energy, let's say house A has a bunch of different solar panels, they're producing energy. House B purely is like, plugging in their EV. They don't really have a solar panels or any sort of production on their end. House A would autonomously or send energy to house B, and then we would say, how does house A get compensated for that?
Yeah,
so in our
like
case,
a public register.
exactly, yeah.
Okay, like they get to choose their own. It's like a decentralized market for energy, but only for the neighborhood, and it just uses blockchain to sell.
Okay.
Yep.
All right, great. Thank you. All right. I left a team, so it's not the final two. We also have, I think, oh, sorry. Penguins of Madagascar is also in. So, all right. So 1 in 3 chances. And mystery eggs. All right.
24.
Yes, it is. So we're Mystery Inc. My name is Dev. I am a sophomore civil engineering student.
My name is Lou. I am also a sophomore civil engineering student.
My name is Sonia, and I am also a engineering student.
Okay. All right. So going into our problem, right? Communities in rural Alaska are right now facing, or they're fighting a losing battle against their environment, right? Many of the homes are built to withstand Arctic climate, but none of them are built to withstand climate change, right? So traditional construction is starting to become too costly and it just takes too long, right? And when we have storms like the typhoon that just hit recently, and we give people like, damage assessment or insurance people that go out there, it takes days. It could take even weeks, and that causes delays, and it causes delays in the funding, and it keeps these societies in this cycle of just damaged towns and infrastructure, just waiting for the next storm to come and hit. So that leads us to our mission statement, which it is to empower remote and climate vulnerable communities with rapid, reliable building insights that speed up recovery and strengthen long-term resilience.
Right, so that takes us to basically what we were coding. So we developed 3 machine learning models. The first one we labeled as our damage classifier. So that one, we actually had to create our data set for that one. Basically just a bunch of images from like the different villages in Alaska, like Kipnuk, for example, and just identifying the level of disaster in those images. So we gave some that had no damage, some that had partial damage to the structure, and then some that were totally destroyed. And then we divided those up so that our machine learning model could train off of that data set. And then we used that kind of blueprint to customize it for our second 2 machine learning models. So for our second one, we did a roof classifier. So the first one is basically just to identify the level of disaster. And then our second 2 would be used for like the reconstruction process. So our second one classifies the different types of roofs into flat gabled or hipped roofs. And then our third one is for building materials, so wood, masonry, or concrete structures. And as you can see, these are our outcomes from our programs. So those 2 were correct, those 2 were correct, and then this one, I just showed one example of how it got it wrong, but we did face some issues in this one, particularly just differentiating between partial and total damage, but that's also like on us because it's kind of hard to classify what's partial and what's total and what's like the focal point of the image and stuff. So.
Yeah, so the way that we collected that data, as Sonia mentioned, there was no existing data set for Alaska, so we created our own by searching through news articles, using Google Earth and state emergency reports so that we can make our own data set to feed into that damage analysis machine learning model. And then for the roof and material ones, we use existing data sets from websites such as Kaggle and Zenodo. So after training those 3 models, we have our results here. Our damage classifier reached 63.64% accuracy. Our roof type classifier achieved 80.17%, and our material classifier achieved 43.94% accuracy. We also have displayed here one of our loss report for the damage classifier. So as you can see, this one, it seems more accurate because we did create that data. It is a smaller data set because we had to search for those ourselves. So it also says down here,
as Sonia mentioned, that the main issue, I suppose, was classifying between partial and total damage, which is expected.
So for the future to improve our model, I think just finding more images to train our data set on to improve the accuracy and just increase that magnitude.
And lastly, we're going to look at our vision as well, right? So the first question I ask is how many more models can we have? Right now, we're only analyzing roofs, right? And then how much farther can we take that, right? Can we analyze walls? Can we analyze foundations or even the landscape around buildings, right? To get a more accurate, damage assessment and potentially even roll that into cost projections, right? Or what the projection is to rebuild, right? For the data set milestones, again, we built our own data set by pulling photos off the internet. So hopefully that you can extend that, right? Not only for Alaskan communities, but look at other, Arctic communities in Europe, Russia, etc., and even go as far as, look in places that are hurricane typhoon prone, right? To analyze damage structures there. Going off of who we use it, I'll try to make this quick. Arctic communities, right? The government, insurance people, that's where it could get used. And then what will we replace? We'll replace insurance adjusters because no one likes them. So that's all for us. Thank you.
So just wondering why the building material, can you find the building materials from maybe some document of the building based on just locations? Why you have to use image?
Oh,
That would go back into rebuilding whenever a disaster does strike. We can classify what kind of material is needed to rebuild those homes in that environment.
And then I think in the future, if it would be possible to integrate all three, so you can just analyze one image, see how much disaster,
what's necessary to
right,
damage,
like how much damage it had, what material it was made out of, just to kind of help in the reconstruction process.
Right. Thank you. Next thing. All right, head down to the last two. I think. Whoa. All right, the green team. By one pixel. Slide number. Found you. Yes, they also picked the same song totally randomly. What is next? Yeah, I can.
Do we just start whenever we want?
Yeah, whenever you're ready.
Okay. All right. Good afternoon, everyone. We are the Green Team. Okay. So our problem. In many rural communities in Alaska, waste management is a large problem. Natural disasters like typhoons, blizzards, and permafrost create or destroy many communities and create large amounts of waste, which end up in landfills. These landfills can fill up very quickly and require locals to burn waste to save space. Locals will also burn waste to create warmth for their communities. Our solution to this problem was to create an AI model that can sort materials and determine the safety of burning each material.
Yeah, so the green team came up with Rec AI. It's a real-time waste recognition software. Here we're gonna play a demo of our software. So it is a user interface. Let me just get the quality. Yep. Okay. So once you click on the link, this will take you to a real-time user interface. Here, the user can upload their image of their trash, and we'll try to input the user's variables, so how much trash they see in the picture. And so once they do that, it will run into our AI software. This will help create a segmentation model where it can see which trashes are there. And then we can also see what the high confidence objects are. So these are above 80%. So the model thinks this is most definitely cardboard, and it has a confidence model of 87%. The ERI is an index that we came up with that is the energy reduction index. So it is how safe it is to burn. So 1 is safe, 5 is very toxic. And we do see some problems with our model because sometimes it's not really right, but our solution for this, we need more data sets, so Alaskan data sets with landfills. And we also input user feedback, so if they can also flag it down in this user interface. Yeah, and then this goes through each one's, and we can see what the objects identified are.
So to go deeper into how our program works, we use 2 different types of models. One, the image segmentation model, the segment anything model, SAM by Meta, and then the ResNet model, which is an image classification model. Basically how it works, image segmentation, it sections the objects that it finds in the image that the user inputs. So it sections each object that it finds, and then it sends it to the ResNet model, which does the classification. So it classifies what types of waste it is, plastic, cardboard, wood, metal, etc. And not only that, it's further trained using over 4,000 pictures of trash from a database that we found. And then we use the same confidence level, over 80%, is what's shown in the final result. Finally, we also have the health index, which we saw on a scale of 1 to 5, 1 being the safest and 5 being the most harmful.
So the impact of our project, it empowers communities as it provides guidelines on how to effectively burn waste. And by providing a health index, and it protects human and environmental health because it reduces the likelihood that communities are going to burn trash that could produce toxic fumes. Additionally, it saves costs because there's not as much trash that needs to be transported out of these communities. And looking forward, we hope to fine-tune and advance the accuracy of our model because subtle textures aren't caught as often. And then by providing feedback to the users on taking a photo closer to the trash based on confidence calibrations and distance, that would also improve our model. And there's a lot of potential for adding additional parameters for what categories can be recognized, and another one is recycling. So with Rec AI, we hope to improve the clean communities and provide safer waste management.
Thank you. Any questions? Yes, sorry. I forgot to introduce this.
Oh, I'm a second year still legendary student.
Yeah, I'm Ritz. I'm a second year environmental engineering student.
I'm Daniel, our second year student.
I think that the question more comment that seems nicely in the future and in the future, if you identify the toxic and maybe suggest to you.
Thank you.
Thank you. All right.
All right, thanks so
much. Right. Our last speaker, we just get on him in. All right. Whoa. Right. Penguins of Madagascar, we have a Lone Star. Slide number. There, found you, right?
Oh yeah, that's good. Back.
For the back here. This is next, previous, another supplementary. Hey, all right, great.
Hello, everyone. I'm part of the team of the Penguins of Madagascar. Unfortunately, today, none of the other penguins could make it. So it's going to be a little bit of a quicker presentation. So the big problem that we were trying to tackle is, as we've heard from a lot of groups today, Alaska has been devastated by this region of Alaska has been devastated by a typhoon and has displaced a lot of people. And we kind of wanted to create a code that would track and visualize where these refugees were going. So we kind of thought of some different ideas, and we explored like an interactive map that could show if whatever number of refugees there are from different towns that were damaged by the storm, where they would end up in this one region of Alaska. So what our code basically does is it takes a PDF of a census map, and we identify the cities that have been damaged. So these are the coastal cities, and by increasing the number of refugees coming from those, it will visualize where they're ending up. And what we did is the code decides where they end up based on the population of the respective town. And so one limitation is that the Yukon-Kuskokwim region does not have a lot of people. Well, there's around 28,000 people, but they're very dispersed in several different communities. The largest town is Bethel. And so for disasters like this, especially with lower numbers of refugees, they'll all end up in Bethel since Bethel has a higher capacity for them. But what we would like in the future is to try to refine this code to make it applicable to other disasters. So we think it'd be really cool to be able to input a map, a census map from a different city or a different region, and then be able to kind of pinpoint where the largest densities of refugees will end up. And so that's kind of what we're looking to do in the future. And so, yeah, thank you very much for listening.
Great.
Okay, do you think that this could be used for finding or distributing where refugees in war-torn countries could go? Like, maybe this refugee camp has all this resources, or this is a demographic, so maybe we want to keep that demographic. This is a population. Do you think that would be actually useful?
Actually, yes. We were looking a little bit into that, and one of the big things that we want to add to the code is to add like food and resource parameters. So I think more data would be necessary, of course, like from whatever refugee camp or town that is hosting them. But I think that would be very interesting to input in this code and pursue.
Yeah, question.
Yeah. To clarify, it's just an optimization problem with one parameter, which is the population of the different cities.
Mm-hmm.
Okay.
And in the code, the map is interactive, so we can. There's like a slider that changes the number of refugees being displaced, and then it'll change the codes or the heat map. Sorry.
I think that'd be really cool in Texas, actually, like with the hurricanes on Texas around the Houston area. Lots of refugees go to like San Antonio, and oftentimes San Antonio is kind of overloaded, especially in the military bases.
Mm-hmm.
So I think that'd be a really cool application.
Yeah, for sure.
All right, thank you so much. Okay, was an amazing set of presentations. So I'm gonna lock all our judges in a room next door until they figure out. I have your certificates, so don't go away. So we're gonna give out your certificates while the judges decide. I'm just gonna take a minute with them and then come back, and Sarah will have the certificates ready. And there are cookies, so in the meantime, go grab some cookies. Right. Ginger.
I get my clicker back. Where's it? Best thing I ever got from a conference, by far. I'm so sick of flash drives and like pins.
There's a conference room. Can you go there? I'll come. Yes. Do you want to hang certificates? Yeah. Okay. Because it will take some time. I thought it's ready, right?
What was that?
The certificates are ready.
Yes, sir.
Yeah.
Do you want to hand them out right now?
Yes, yes.
Okay, do you want to tell everybody to like sit down?
Yeah, give them a few minutes and then, yeah, we can have. Alright, if you want to take a seat, I'll start giving out certificates. Yes.
There's still more and I'll review them.
Okay. I can do this. I think it's, yeah. All right. So I have Sophia, Duna, Sophia. I think. Wait, what team is this? Sorry, say that. Yeah, that's you. Yes, I was looking for you. Oh, we're just giving out certificates and not giving prizes yet. They're still deciding. I'm giving out certificates. If you want to stand here and get certificates, take action. Okay. All right.
Can we take a picture?
You can get a picture.
Wait, let's do it. Oh, you mean you're taking photos? Oh, okay.
Take a real picture.
Oh, okay.
Alright, next team, if you want to line up. Lucas, it's like, oh, these, come on, please, like, look. So we take pictures. Jingle bells. Alright, jingle bells. Do I come your certificate and picture? Jingle bells. Right here. Penguins of Madagascar. Madagascar. Everyone.
Thank you so much.
You want to take a picture?
Oh, everyone.
Everyone. It's not.
I do.
So which teams? Yvonne, Sophia, Jonathan, second team. Right. So come over here. And then Samir. Here.
So, do you want us to be your penguins?
Wild crackers. Wild crackers. Who am I missing? Like, who hasn't got the certificate yet? Oh, yeah. The green team.
Yeah.
You don't have to. Last year.
Oh, last week.
Yeah. Yeah. And Pokemon. Alright, so yes, after that.
Okay.
Sure, like, we do all. Yes.
That was the goal. How about this? Y'all want to do it again? I'll never do it for y'all.
Everyone ready? Is everyone ready? Okay. Well, I'll let the judges come in. Right? All right. I was going to give out like the best mentor prizes, but unfortunately we have a tie, which means the mentors will get their prizes later on. So collect your Legos. Sarah will be surprised that we need more Legos later. I'll talk to her. So let's go for. So we have a joint third prize. There is a tie. So there are two third places. All right. So there's in no particular order for the third prize. Congratulations. All right, B. Come over. Hey. All right. So the second third prize are tied. Ready? And congratulations, Wildcrackers. All right. Thank you. All right, you want to take pictures?
Oh, yeah.
All right. All right. For the second place, we have, I forgot, the green team.
Yeah.
Right.
Thank you.
Hey, and after 5 days of grueling hackathon, we finally have the winner of the fall 2025. Congratulations, EV3. Do you have another member? Yeah, please. Thank you so much. Thank you. So I have my mentors to give to. But yeah, next. All right. That's a wrap, and I'll promise my mentors I'll get you Legos soon. And thank you all the judges. Thank you so much for participating, making it a fun event. I hope you all enjoyed it. And thanks Sarah and her team for feeding us for the last 5 days. Right. And thank you, Jeff, for all the pictures. All right, have fun and see you. All right, do we take a picture?